alloy that is a little more effective, more complex to form is of course more, it have more strength, has more corrosion resistance, is better for abrasion. Of course, is even better than stainless steel in this part, and it has a long-term biocompatibility. It means that it will react in a very, very low kinetics in terms of degradation that can produce any compound that can be toxic for the body, right? Disadvantages, of course, if it's a very good alloy, it's gonna have very high young modulus, and of course, it's expensive, right? We can see here some metallic alloys used in biomedical devices and screws. So implants, we can see here how the screw is done here, and it reflects in the X-ray. Okay, how we mitigate the corrosion on biomedical devices? There are four interesting techniques that are trying to mitigate, right? Because it's difficult to stop, because at one point everything's going to be corroded. But if we apply these techniques before the application of the biomedical metallic device, we can have a better effect and a better lifetime in service of the material. So we have the great chemical treatment, surface preparation, passivation, and polishing. What is the chemical treatment? We have different type of chemical treatments actually to reduce the magnitude of printing corrosion. For instance, the D6AL or the grade S5 STM titanium. So we produce some nitriding chemical treatment in order to cover the surface and make it gray. If we focus on surface preparation, we have improved the resistance to wear, and when we have wear, sometimes it accelerates corrosion. So if you have a very well prepared surface, like with little defects, let's go like that, I think, or not think, it is proof that the resistance is gonna become better. Passivation, some chemical treatment also improves the growth of forms of sites that can be passive films, and they are formed to be protective layers in order to have more resistance or more corrosion resistant to the environment. And polishing, if you remove the scratches on the surface, you have a better surface finish, and it will help in remove the stress tracer that the scratches are doing in the surface. So polishing is actually very simple, and it helps for mitigate corrosion, yeah, because it removes the scratches that could act as a stress erasers. Okay, we have also some metallic materials that they are bioabsorbable, yeah, like magnesium. Magnesium and it alloys, they are good because they are like temporary implants. They are used to make stents, but magnesium is very reactive. What I mean that magnesium is easy to corrode, right? Anyways, the corrosion products of magnesiums are kind of bioabsorbable, and they are kind of degradable, and they don't make that much toxicity on the human body. So they are used for like an alternative temporary implant. So what I mean, you can have a corrosion of them, right? Because it is known that magnesium can corrode from the physiological pHs from 7.2 to 7.4. But when someone is designing an alloy that is going to be used a bioimplant or an implant or a prosthesis made of magnesium, it has to take into account that the magnesium has to last until the patient is healed, right? So we have to consider that magnesium is gonna degrade inside, it's gonna become, it's gonna be absorbed, right? So when you design an implant that is made of a magnesium alloy, you have to design it in terms of Okay, this is the healing time. This is the time that magnesium can resist or can be used inside the tissue or in the human body, and you have to design and propose the design for that, right? If we think about ceramic biomaterials, they are generally used. Why? Because they have a lot of hardness and they are very good to resist the wear, right? If they are very good at resist wearing and also they have hardness, it's easy to understand that they are used for joints and teeth, right? And tooth. So, teeth, sorry. So some common ceramics include, or the example for ceramics are alumina, silica, zirconia. All of them are oxides that they have very, very interesting properties that are the reason that they're used in biomedical applications. We can see here some advantages of these ceramics. They have good wear characteristic, even more if they are associated or they are mixture with polyethylene. They have high compressive strength, they are chemically inert, that's a very good thing. They cannot be soluble, and for sure they are very, very biocompatible. So what are the disadvantages here? They are brittle, they have a low fracture toughness, high modulus young, they can be low in tensile strength, for poor crack resistance, and some of them are very expensive to have, right? You talk about composites, yeah, they are expensive. You can see here on the left hand side how they can change in terms of wear resistance when they are mixed in composite materials, metal and polyethylene, ceramic and polyethylene, only metal and ceramic. They are not that, they are getting very good when they can be combine each other. And ceramic is really, really good. Okay, so plastics, yeah, plastics are everywhere, from every kind of industry because of their flexibility, stability. Some of them are very inexpensive, and they can resist many, many environments, and they are easy to produce, some of them. So plastics are everywhere, right? Even in biomedical applications. We can see some biomedical examples here from even the capillarity that is used from the contact lens. Some parts of the implants are made of plastic, and we can have a very, very important part here. Even some drugs like the medicines, plastic are used for the benefit for encapsulation and stuff of these drugs, and also it want to help in the transport for the final application. What is it? 934. Okay, this is a very important one. It's the ultra high molecular weight polyethylene for this. We can call it UHMWPE. Yeah, it's ultra high molecular weight polyethylene. It's a very good biomaterial for biomedical application. It decreases fatigue and fracture resistance. What are the advantages of this material? This is strong, is ductile, is resilient, and is resistant to wear. The problem with this ultra high molecular weight polyethylene is that it's susceptible, it's not very good to abrasion. It can have some fair body inclusions when it can be wear. Of course, it's weaker than bone intention. So you can play with some properties, but you have to take into account, as I said before, good advantages, but also the disadvantages can influence or can have a very detrimental impact if they are not taken into account. Here we have some examples in which you have metallic, polymeric, and metallic biomaterials used in hip replacement, right? Also some ceramic components, and this slide makes us understand that we have to combine different material properties for different part of the implant or the prosthesis to make it better, right? To make it work better. We play with the material properties, with the polymers, with metallics and ceramics, maybe composites as well, in order to get the best performance product, right? That's the complexity of this area in design is that you have to take into account the biomechanics in materials in order to get good performances and also a final product that can resist wear, fatigue, corrosion, and it has to be biocompatible, right? So it's a combination of material science with human physiology. Okay, how materials fail then? We have seen that many materials can be used for the biomedical application, for the biomedical engineering, for medical devices, have to be input in the patient or in the human body of someone that is in need. Yeah, but we have to characterize them in terms of how they fail, right? We have put it into focus or highlighted these three: corrosion, fatigue, and wear. Right? What is corrosion? It's a simple definition, is an electrochemical reaction in which the material, basically a metal or an alloy, is removed, dissolved, oxidized from the substrate, right? What is fatigue? Is a progressive failure of the material due to the application of a cyclic stress, and after that, this stress could get a failure in the material, right? Because of fatigue. And the wear, wear is the removal of the material from a solid surface due to a mechanical action, like wearing things. So these three highlighted material failures are very common in the application of biomedical implants and in biomedical engineering, right? We have here a type of corrosion that can be spotted for the first sight, even with visual inspection, that the surface of the material has been corroded. That is not good, right? We have this type of corrosion that can happen inside our bodies, right? We have galvanic corrosion. What it means is the corrosion that happens between two different materials being used and they are being connected together. For instance, we have stainless steel screws with a titanium plate. Of course, these two materials are going to have two different electronegativity, and one is going to act as an anode and the other as a cathode. And in the anode, you're going to have an oxidation reaction that can produce corrosion products, and they have an impact on the final material performance, and also it can be very dangerous for the toxicity of inside our bodies if we have corrosion products inside them. Stress corrosion cracking, it presents failure in form of a crack, in the microstructure due to stress and corrosion. It's a very common failure mechanism when you have stress in the materials because of the movement of the body. The implants have to be resistant, or they have to perform some different moves, loading bearings and stuff. So stress corrosion cracking can happen. Some fretting corrosion also happens. It is when you have fretting against the movement against each other. So fretting increase the corrosion rate, and you're gonna make the material fails faster. And forbidden corrosion is kind of a local form of corrosion when you find some pits in the material. They can happen because of many things. In the human body, it could be a crevice that have been created in which the microenvironment created inside the crevice generate the pits, and then pit corrosion can happen. Yeah. Okay. In this table, we have divided some type of corrosion in different implant location and the different material that we can have, right? If we can see here, we have dental orthopedic alloys made of 304 stainless steel or for a cobalt-based alloy, and it can fail with pitting corrosion. If we use 316L stainless steel for a bone plate and a screw, some crevice corrosion here where my blade can happen because it's a different microenvironment that can have oxygen differential aeration, or it could be more acidic because of the anodic reaction. Everything can happen in microenvironments. Even it could be very aggressive in terms of the entire material. So crevices and pitting are aggressive as well. Corrosion fatigue, of course, for bone cement, the implants can be done with 316 stainless steel, cobalt and chromium nickel iron alloys. Fretting in the ball joints, it can be fret because of it movements and stuff. You can have galvanic corrosion. This is easy to understand why it could happen in oral implants, in screw and nuts, because of the combination of two materials that create the galvanic cell. We have before, right, when it was used mercury, gold, and these kind of things in oral implants, you have selective bleaching of mercury, right? So these kind of problems they can happen on the materials that we have seen in the lecture, and also if you have one of them in your bodies, these things could happen. What happened with the cardiovascular inputs, right? They need, of course, to be blood biocompatible, right? Because they're going to be exposed to the movement of blood, and the material need to be biocompatible to don't be rejected from the body and don't cause any toxicity, right? Or any adverse reaction for our bodies. Stainless steel, chirurgical grade, medical grade, titanium, they're memory shape alloys, some cobalt, the chromium. They are very used in stents for the valves and for the valves as well in the heart, right? What can or what are the detrimental facts of using these biomaterials? Okay, we know that they can fail, they can corrode at one point, something could happen. In particular, when something is getting corroded, some ions of the alloys can move through the immune system. Imagine that you have a stainless steel stent, and this stainless steel, chromium, and all these ions can move from the material through the local body, to the body of the local person, and it can have a reaction, inflammatory reaction, and many responses of the body trying to complain about this situation that is happening inside the body, right? In terms of memory shape alloys, the nickel titanium alloy, it's a very good one. It reminds the shape of the memory effect, and they're even also very good for corrosion resistance. Here we have a slide in which we can see some corroded stents inside of an artery or a vein, right? More or less, a corrosion spot can be done always when the geometry is kind of difficult, in which a specific microenvironment can be formed. You can see here in the joint of the stent, basically it's a good spot for corrosion to be found. So it makes us to understand that structure properties and its functionality are also very related, like any material. When we study material science, we have to take into account that difficult geometries can influence microstructure as well, and microstructure can influence properties. So that's one of the reasons that basically when we find difficult geometries on stems, they can be good spots for corrosion. Okay, corrosion of dental implants. The problem here is the mouth, right? The mouth can have different types of pHs. So the pH is a very, very important key parameter for corrosion. You have to understand that saliva can change temperature as well, the quantity of saliva. And in this part in the mouth, we need to understand that it would be a very, very strong and aggressive environment for corrosion of dental implants. They can have pitting corrosion, galvanic corrosion, and stuff of corrosion. So we have to think about this because if we can stop that kind of corrosion, we can lead to stop releasing carcinogenic agent from the alloys, right? This is one of the most detrimental parts of corrosion by biomedical engineering in the mouth, right? Titanium is kind of good for its big corrosion resistance, and the uses of precious metals like gold, palladium, and platinum is not only aesthetic because okay they shine and stuff, but their electrochemical properties in terms of corrosion they are very 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 good at corrosion resistance. Very difficult to analyze or oxidize gold, for instance. So in terms of okay aesthetic properties, they are nice as well if you like golden tip, but they are also good for corrosion protection. Right, I think I have 2 minutes. I guess I have just 2 slides more. It's about the orthopedical implants. I'm gonna be very fast with this. It's like, let's say, called hip replacement, shoulder repairs, clean out knees, toes, fingers. Here we have to think about more in wear, right? In wear and fatigue and fatigue. Why? Because they are in constant move. Yeah, this kind of wear can turn into accelerate corrosion. So you keep wearing, you keep moving your implant, your prosthesis, and this movement, this fatigue, this cycle stresses, they can influence directly in the corrosion resistance of these alloys. So basically, for engineering design, you have to put that into account. It's called biomechanics, and it's preferred to select alloys that are or composite ceramics and plastics, polymers, sorry, that are very good in this type of wear and to stop fatigue, etc. So we have different combinations: metal and plastic, metal and metal, ceramic and plastic, and ceramic and ceramic. They are different. They how you can see here, they are combination of metal and plastics, metal and metal, and the wear decreases. Then we have ceramic on ceramic, even more. They are expensive, of course, but if you see the wear in millimeters per year, is even better for stopping it. And of course, we have different combination of metal and the amount of money and by that. Yeah, for this is a metal alloy that is covered with a smooth black ceramic surface. It's called oxyneum and is for 5,000 times better in abrasion. So it's very, very good to reduce wear. These are implants, these balls made for this oxyneum, and they are very good. They decrease the wear reduction in 98%, so it's a very good thing. Okay, for conclusion, very simple conclusions for today's lecture. We need a lot of information for implants and materials to be to do a choice for which one the patient is gonna need. We know that corrosion is one of the main processes that can when you alloys in the implants of the human body. And we have to also take into account that it's not only corrosion, it's a lot of wear, stress, biological toxicity that can happen because of bad selection of a material. So that to make into account. Thanks, muchas gracias. Este es mi correo electrónico por si tienen alguna duda o si quieren conectar por LinkedIn pueden tomar la foto de este QR code que les llevará directamente a mi página web. Sí, eso ha sido todo. Me pasé un minuto, creo. Disculpen.
No, perfectamente bien. Una vez concluida la exposición, damos paso al ciclo de preguntas, por favor. Eh, Quienes deseen realizar preguntas pueden hacerlo en este momento.
Anita, están levantando la mano.
Y 10, la elaboración del
Sí,
informe de etapa
no.
de planificación. Cada una de estas etapas cuenta con sus respectivos responsables. Entonces, en el punto 1 al 4 es la parte
Mientras tanto, Anita, adelante,
Ya,
Cristian López
perdón.
nos está
Sí.
solicitando palabra.
todo esto fue realizado por la Comisión de Examen de
Sí, muy buenos días. Primero que nada, felicitar al profe Raúl por su excelente ponencia. Estamos orgullosos de que como estudiantes de la Universidad de Chaitec tengamos a tan gran representante nuestro. Y mi pregunta es, por ejemplo, ¿cómo sería la corrosión para sistemas nanoestructurados? Por ejemplo, yo tengo unas nanopartículas metálicas o magnéticas y las introduzco dentro del cuerpo, por ejemplo, para hacer drug delivery. ¿Y cómo sería el mecanismo de reacción para que esa nanopartícula sea expelida del cuerpo? O sea, ¿cómo podría sacarse esa nanopartícula de nuestro cuerpo sin producir una reacción alérgica o inflamatoria?
Hola, Cristian, es bien difícil la pregunta, pero es bien buena. Verás, las nanopartículas también van a reaccionar como cualquier metal a las reacciones electroquímicas, ¿sí? Entonces, si la estabilidad de la nanopartícula dentro del fluido corporal, en las condiciones fisiológicas de tu fluido, no generan oxidación, es decir, en las nanopartículas no se da una oxidación, tú tienes que hacer énfasis en la biocompatibilidad y en la toxicidad de la nanopartícula como está en la que tú tengas, si es un óxido, qué sé yo, un hidróxido, alguna partícula en función. Pero por el otro lado, si tú tienes una nanopartícula metálica, ¿no es cierto?, que genere una reacción electroquímica y tú puedas generar una oxidación y esta reaccione con, qué sé yo, con el cuerpo, te va a generar toxicidad. Lo que se puede hacer, yo te recomiendo, es hacer un ensayo electroquímico de polarización en un fluido similar al del cuerpo, en donde vas a hacer la aplicación de tu nanopartícula y ver si esta tiene tendencia a novizarse, a oxidarse y bueno, saber después qué tipo de óxido es y buscar a ver si es agresivo con el cuerpo, si genera algún tipo de reacción de la parte inmune, ¿no es cierto? Algún tipo de cosas con el cuerpo. De salirte negativo, o sea, tu investigación quiere decir que incluso aunque tu nanopartícula reaccione con el pH fisiológico, con los agentes de los fluidos corporales, va a eliminarse tranquilamente sin tener problemas. Del otro lado, si es que te sale algún tipo de nanopartícula, un óxido de esta nanopartícula después de reaccionar con los fluidos del cuerpo, te sale algo tóxico, como digamos, qué sé yo, algo con cromo, etcétera, es más difícil y por lo general se busca cambiar de factor, o sea, de nanopartícula. Eso, pero se puede hacer, con electroquímica se puede hacer, un potenciostato por acá y podemos probar.
Listo, profe, muchas gracias.
Gracias, Cristian.
Perfecto. ¿Alguien más desea realizar alguna pregunta? Sí, sí tenemos a alguien más
Doménica.
Sí, por favor, damos paso a la siguiente pregunta. Me parece que...
Si lo subió bajo la mano ahorita, era Doménica Espin.
Ah, ya,
Si
sí.
es que desea realizar la pregunta, puede abrir directamente la audio. El micrófono, por favor. No, parece que no. Adelante,
No,
Daniel.
sí.
Hola Raúl, buenos días. Nada más
Hola
que
Dani, ¿qué
pregunta,
tal?
nada más agradecerte por siempre por tu predisposición para con nosotros la Escuela Superior Politécnica de Chimborazo. Decirte que tenemos un gran recuerdo tuyo y felicitarte por este nuevo tema de investigación que lo has sacado, me imagino, por allá. Desearte el mejor de los éxitos y esperamos contar contigo en una próxima oportunidad.
Gracias, Dani. No, y ya sabes, bueno, ¿qué más que decir? Tanta ayuda que me brindaste desde cero, siempre con la disposición y el profesionalismo que tienen, sobre todo en la carrera de ingeniería química. Obviamente estoy feliz de estar acá, mucha motivación. Y ya saben, estamos para colaborar a las órdenes, la investigación no se hace solos. Entonces, feliz de verles, de ver la mano a los tiempos también. Entonces, chévere, chévere, ¿no? Espero que pasen bien. Ojalá nos podamos ver en persona algún rato, organizar esto en presencial también sería muy chévere. Entonces, pero por ahora está excelente, Dani. Gran trabajo a la organización, a los coordinadores, a los decanos, etcétera. Como siempre, muy bien. Y muchas gracias por esta oportunidad. Espero verlos pronto, sí.
Muchas gracias. Me uno al agradecimiento de Dani por la excelente participación, doctor Raúl Davas. A continuación voy a proceder a la lectura al correspondiente certificado de participación. No sé, Marlito, si me ayuda, por favor. Sí. Escuela Superior Politécnica de Chimborazo, certificado de participación al ingeniero Raúl Dávalos, PhD, Cuarto Congreso Internacional de Ingeniería Química 2022, por su valiosa y destacada participación como ponente en el Cuarto Congreso Internacional de Ingeniería Química 2022, con una duración de 40 horas académicas realizado en modalidad virtual, del 30/05 del 2022 al 01/06 del 2022. Firma Dr. Celso Recalde, decano de la Facultad de Ciencias, la ingeniera Mabel Parada, coordinadora de la carrera de Ingeniería Química, ingeniero Daniel Chuquín, coordinador del evento. Mil gracias por tu excelente participación.
Muchas gracias, ¿no? Qué chévere.
Igualmente, Raúl, saludarte y agradecerte a los tiempos, igualmente verte y felicitarte que estás por allá también en este nuevo, en esta investigación que estás realizando. Te felicito y pues muchos éxitos. Esperamos verte pronto por la universidad compartiendo conocimientos. Que pases muy bien.
Claro, sí, chao chicos, muy amables,
Bien.
¿no? Que pasen bonitos.
Que pasen muy bien. Hasta luego. Nos vemos a la siguiente ponencia. Agradecerte, Raúl. La siguiente ponencia pues la tendremos a las 10:30. En este momento comparto la charla que vamos a tener para que por favor estemos pendientes. Muchas gracias.
Recording stopped.
Lo que sí, por ejemplo, se analizaron 1000, de los cuales
el punto 6 ya se envía, mejor dicho, a los docentes la matriz de observaciones, porque como si es en el próximo mes la prueba, todavía falta algunas etapas que sería importante. Eso nomás, compañeros, gracias por sus observaciones, y yo en este caso me retiro porque tengo una defensa en 10 minutos. En este caso, como ya hemos hecho una revisión de los reactivos, el informe ya casi lo tenemos listo. La idea es tener este informe ya cuando se consolide también la parte de la colección por parte de los docentes. Entonces, para mí, ahí hay que enviarles un oficio a cada uno de los docentes informando estos cambios que tenemos a nuestros servicios para que se pueda generar una de las fechas que se deben enviar ya con la colección. Eso sí, ya tendríamos el informe completo. ¿Hasta cuándo les damos de plazo? Yo creo que solo una semanita nomás hay que darles para que tengamos pronto esto, porque no estoy segura de qué fecha es la que se van a tomar los exámenes de conocimientos. No decía todo el mes de junio, pero no especificaba nada. No especifica, no ha habido un específico, entonces... El sábado y el domingo le damos como posesión, porque nos podemos poner hasta el domingo, porque le decimos trabajar hasta el domingo, porque estamos explorados. Y inicia el proceso, porque ya cuando establezca la fecha, hay que no nos han de poner el 14, sino de poner una fecha, digamos, entonces ya cuando se establezca la fecha, hay que considerar lo que habíamos visto la vez anterior, que dijimos para hacerles un repaso a los chicos, pero un aula. Hacer una simulación. Exacto, entonces eso es lo que vamos a hacer. Sí, para que se pueda manejar. Eso es lo que está, como dije, urgente, ¿no? En ese sentido de tomar en cuenta. De ahí las otras cosas, pues ya se las ha venido, digamos que revisando, ya se ha dejado entregando la información que han pedido, y revisando las otras pedidas también por las comisiones, y como le dije también, incluso la comisión de actividad, si hay algo más de lo que no tiene, bueno, que se tiene estudiado toda la información, me preguntan porque, por ejemplo, la calificación complementaria y académica es algo que me está viendo. Entonces, de pronto necesitan finalizar más para poder realizar la documentación que se tiene ahí y se les entrega. Entonces, todo eso ya está conversado, ¿no? Entonces, de igual forma, cualquier cuestión que se necesite, pues el ministerio también de contacto. Eso nada más, también les también era por eso, Angelina. Muchísimas gracias también por acompañarnos en la reunión. Conjuntamente con los compañeros, pues, elaborar también por una revisión siempre, ¿no? De objetivo, y por parte de esta representación de estudiantes, pues tendría que ver también sea la vocera de esta forma, cómo se nos lleva a cabo este proceso del examen de conocimientos en ese sentido. Bueno, creo que eso es todo, amigos. No me queda más que agradecerles y estaremos en una próxima fecha conversando. Muchísimas gracias. A mí unos minutos de discusión de la para conversar también con los míos. Sí, sí.
Igualmente, feliz viaje, Lolita, y esperamos el recuerdo.